Hello students, I'm Argen Kukitaev, and this is a lesson on delta method. It's a method which can be used to approximate the variance of an estimator, which itself is a function, a nonlinear function of a set of other estimates of say regression model. It doesn't have to be necessarily regression model, it can be ARMA, as we will see in this example. Time series models and so on. So the delta method is used not only in time series obviously, but in statistics quite a lot. Again, it is an approximation. So in this lesson we will apply it to a very simple example where we will fit ARMA, autoregressive moving average 1-1 model, ARMA 1-1 model. We will fit it to inflation series, United States PCE inflation series, and the inflation series fit will produce us two coefficients, C and phi, autoregressive coefficient and the constant. Then we will estimate the long run mean or unconditional mean of this process, which is equal to this ratio of the estimate of the constant divided by 1 minus phi, which is an autoregressive coefficient. So you see this is a non-linear function. So if it was something like C plus phi or some sort of a linear combination, then we would have known what to do here easily. In basic statistics, we have the estimates for linear combination of parameters. But when it is non-linear, there isn't a ready expression. So we will have to derive it. And in this case, we will apply this delta method to approximate the variance of the estimator, of this estimator, sampling estimator. Because remember, the value of this estimator depends on the data set. You know, like when how do I say, it's a function of a data set, and thus this is estimator value itself is a random variable. And as a random variable, we not only can calculate its mean and median and so on, but also like variance and other characteristics. So we want to know what is the uncertainty around this long run mean. We will do a couple of other interesting things in this lesson. We will also compare this estimate to the bootstrapped version. So this lesson also includes a brief lesson on bootstrapping. Why don't we start? So well, the prerequisites for this lesson is for you to know what is variance covariance matrix of coefficients of a regression. So when the regression is producing coefficients C and phi, it also will produce the variance covariance matrix. So you need to understand what is the meaning of this covariance matrix. It's good to understand what is a gradient. Without the gradient, it's hard to understand the problem. And Taylor expansion, Taylor series. And finally, we need to understand what are the expectations and variance of estimators. These are all these subjects which I cover in my statistics and matrix refresher for my classes. So let's start. So we'll start with the setup, and the setup here is downloading the data and fitting the model to it, right? So we are going to download the data from Fred service. So if you're not familiar with it, it's a very convenient service database, right, where you can basically find a lot of economic time series. So if you don't know it, you better learn about it, right? So we are going to download the series which have this very long mnemonic, but it's basically PCE or personal consumption expenditures inflation. So this mnemonic, this link actually leads directly to the series here on the website. You could actually download it manually. So for instance, if you're working on Python on your own laptop, you can download this manually and then load it into Python. But I will show you how I do it. I grab it directly from the website, so I don't do any processing here. So you see the output comes right in the percentages. So you can see 3.54. It means the inflation for Q1 2024 in this case was 3.4%. That is an annual. It's an annualized compounded version. So it was actually calculated quarter over quarter, which means in first quarter it's going to be end of March versus end of December, right? How the personal consumption expenditures changed percentage wise, and then we compound it, make it an annual. So for each quarter you are going to get the annual number, right? And you see we get quarterly data. It's quarterly frequency, right? Now why we're using these series, because we wanted to play with very simple time series model, and I chose something called ARMA, autoregressive moving average one. And ARMA model is pretty good fit for inflation series. And we know, why do we know? Well, because the Feds say, they announced it in January 2012, the Feds, Federal Reserve Bank, right? They said that Federal Reserve Board of Governors, they announced that they're going to target 2% inflation. And you may or may not know, United States doesn't have a central bank. It has Federal Reserve Bank, which serves as a central bank. And that this body, it's somewhat non-government body. If you think about it, it's like a strange it has an interesting status. Actually, it's under Treasury in a way. It's the Fed chairman is appointed by United States president, but it's somewhat independent from the actual government. Right, so they said they have like a multiple goal mandate. Right, so their purpose is to maintain money supply in a good form, and one of the announced goals is inflation. So they're going to control the inflation, and in January 2012 they made it explicit that they're targeting 2% inflation, and then they actually said it's going to be personal consumption expenditures inflation. That's why I chose these series, and ARMA series, this model which we will be fitting, it's a stationary model, and for a variety of reasons I think it's a good fit for this series. Anyhow, we will download the data using Pandas data reader in Python, and you just open the data reader, and then in our case you don't even have to put start date, but I put start date at 47. I grab the whole thing, I say Fred, right, meaning that we're going to get it from Fred, but I will then cut the data out from January, right? So here's the series from 47, just to get an idea. You see, it's been going quite high, inflation, like in 80s, you see 12% and so on. In 2020, during COVID, under Biden administration, it shot up to like very, very high values of if you looked at PCI, personal, what is the other index? Sorry, CPI, Consumer Price Index, inflation, that went to like 10% area and so on. So inflation was very, very high. So the Feds will be playing with the rates, basically increasing the rates and doing other stuff through their market operations to bring the inflation down, because their target is 2%, right, somewhere here. Now I'm cutting out, as I said, the data before 2012, and the reason being is because before 2012 the Feds kind of was hiding. They were kind of they were coy about the actual numeric sort of target, or whether they are actually targeting the inflation. I mean, we knew they have to control inflation, but do they have like a numerical target or not? So they were sort of cagey about it, but the economists kind of figured that the Feds are targeting 2%, but then in January they made it explicit. So that's why I'm using the data only from the moment when they said, when they announced the explicit inflation rate. So notice how in Fred data series for this particular, well, in general for series like for quarterly, monthly, and so on, the Feds mark the date of the quarter as the beginning. So this is a quarter one data, and you see it's January 1st. So this is different from other sources such as Bloomberg. So if you're using Bloomberg, in Bloomberg usually the quarterly series are marked by the end of the quarter, often last business day. All right, so when you're using variety of sources, just be careful with that. But for Fred, it's again beginning of the quarter, so that's why this is a Q1 12/12. Anyhow, so you see I'm cutting the data out using this syntax, like this phrase, right? So I put the start date and two columns, and then pandas will use only the data after January. And at the time of my running, the last data point is 2024 Q1. And you can figure how many data points are there, right? 2024, it's about 12 years and plus one more, right? So 12 years by 4 is going to be 48 plus one more quarter, 49. So the data length should be 49. 49 data points is by no means a large data set. By the way, in statistics, it's you can work with it, but it's not a large data set. So large data sets in time series in economics is like hundreds, but this one is big enough for us to work with it. Now I'm going to fit ARMA 1.1 model to it. So ARMA 1.1 model has this kind of a form, standard form. So there is there's not much interesting here. I mean, you've seen it if you studied time series, but there's interesting case here is the constant. So the model which I'm fitting has a constant. Typical or like classical ARMA model does not have a constant, right? So you have this y and then the other stuff. So what happens if you have a constant? So you can treat this constant actually as an exogenous variable. So you see y, the series inflation, right, is an exogenous variable. And it appears on the right hand side too, and then you have these errors, epsilons. Now c is a constant, some kind of a constant trend. So you can treat it as an exogenous variable like this, right? So you can say, well, my model is like this, except your intercept is going to be a basically very simple model, like in linear regression intercept, right? It's xt equals to 1. So it's like a column of ones in the regression. So think of your regression where there's only an intercept and nothing else, but this is an exogenous variable. You can treat it as an exogenous variable. And actually that is how this class works. Class ARMA in stats models package in Python. So if you're familiar with time series packages, stats models time series package in Python, then you may know about ARMA. So if you add a constant here, it will be treated as an exogenous variable, right? And then ARMA will say, well, that's an exogenous variable, and that's why I am not fitting this model there. ARMA will switch into a completely different model, which is called regression with ARMA error. So what will class ARMA do? It will say, well, this is my exogenous variable here, and then this is my model, right? But then my errors new are going to be ARMA. That's why it's called regression. You see there's a regression part, but errors are ARMA, or in this case ARMA. It is not the model which I'm trying to fit, right? That's why this class ARMA is not suitable for me from stats models. But stats models has another class called SariMax class. So what SariMax class does is the following. If you are adding a constant, it will not treat it as an exogenous variable. It treats the constant and time trends separately. It has like a special treatment for them. So it will not switch into regression with ARMA errors. It will fit the ARMA which I want, ARMA model which I want, which is this model. So that is going to be the class SariMax. Again, if in SariMax you actually add a bona fide regress, like an exogenous variable, which is not a constant, but some, real regress, like it could be money supply or whatever, some other real variable, then it will also switch into ARMA or rather regression with ARMA errors. But it will not switch to that mode on just a constant. If it's a constant, it'll run this guy. So that's why I'm going to use this class called SariMax, and I'll fit into my model, my data, sorry. So my data Y is going to be exactly that, right? It's going to be PC inflation, not the index of PC, but the inflation itself, that number, 2, 3, and so on, right? I will be estimating in my model these parameters. Constant, I will be estimating phi, I will be estimating this theta, right? It's a moving average moving average side of my equation. So this part is an autoregressive part, and this part is a moving average I'm showing on screen, right? Okay, so how do we fit the model? I mean, I'm not going to go line by line here, but it's very simple. You declare your model, SariMax in this case, this class from state space package called SariMax. Y is my data, as you remember, my 49 points of inflation. My order is 101. So why is the 0 in between? Because this is an integration. If this was a different model, ARMA, then this would not be 0. But this integration is in the middle. I'm saying 0. So the first parameter is autoregressive part, and the last parameter moving average, and in between differentiation. So this is a sort of standard way. Almost all software uses this convention to estimate the order of our model. Okay, and then I'm saying trend C. Remember, so there is this special treatment of a trend, and in my case, my trend is simple constant. I could actually put a time trend if I want, but it would have been a very different model. So in this case, I'm assuming this is a stationary model, right? So I'm assuming my series, inflation series, are stationary, although they look kind of crazy here. I'm saying, well, they're stationary because I suspect that, well, not suspect, but because Feds themselves said that they're going to control this. They're going to keep it close to 2%. So it's going to be around 2% somehow, and that's why I'm assuming it's stationary, although the variance may go off from time to time. Okay. Right, so I do that, and then I fit the model, and then the fit results go into the object called fitRes, and then I'll print the summary. So let's see the summary. Well, the intercept, which is our constant, is 0.38, and my autoregressive phi is 0.83. So it's quite far from 1, so it's not an integrated model. Seems like the fit is quite good, right? Then I will print all my parameters here, and then I'll calculate finally this long run mean, right? So I can estimate for this process of the long run mean of my y variable, of my inflation. So I suspect, or I want, or rather I'm testing that this long run mean should be 2%, because Fed said they're trying to keep it at around 2%. So the estimate is like this. I showed it in the very beginning of the class, right? So my estimate of a long run mean estimator is this constant divided by 1 minus phi, right? So our constant here is 0.38 divided by 1 minus 0.83. So it comes as 2.31. Now I can also estimate another quantity, right? I can estimate variance of my series, unconditional variance of my series, of my y variable itself, and there is a formula for it. Where is it? So actually I calculated dispersion here. The formula goes like this. Basically it's an estimator of the variance of the errors divided by 1 minus phi squared, right? And then there is another component here. So if I estimate this amount, then it's a standard formula from equation from time series, so I'm not going to derive it here. But long-running dispersion, don't forget to take a square root, is going to be 195. So it's a pretty big dispersion, by the way. It says that my y variable has a lot of variance, and we already noticed by looking at it, right? So we already know it, so we just got the exact number. But the estimator of the mean is interesting, right? So I got this estimator of the mean, and it says 2.31%. So my long run mean of inflation, 2.31%. Great, but it's different from 2%. The Fed said it's 2%. So what does it mean? Does it mean that my model, does it mean that, well, Feds are not doing very good job of keeping at 2%? Is that what it means? Well, here's the problem. Yes, I have this estimator, right? But how good is this estimator? Like what? Like how precise this estimator is? We don't know. So I would like to know what is the variance of the estimator. Now, I already calculated, I've shown you the long run dispersion of the variable itself. Great, well, it tells me a lot of noise, but it doesn't tell me much about the dispersion of the estimator, not of the series themselves, but of this estimator, which is a non-linear function of the coefficients of the model. So if this was linear combination, this is not linear, but it was linear, then see, when I estimated my model, I also obtained a variance covariance matrix of it. So I would have been able to use not only the parameter estimates, but also their variance covariance coefficient to get the variance of that estimator of the long run mean. But this is a non-linear combination, and I cannot do it. So I need something, some other method, right? So this is this is what I'm talking about. So these reds are observations, blue is my model fit predicted, right? Dotted line is my long run mean, estimator of my long run mean. Now the dark, the solid black line is the 2% target. So there is some discrepancy here. However, again, the variance is large, so I'm suspecting, well, maybe there's a lot of uncertainty about this estimator of 2.31%. So the rest of this lesson, or at least the half of what is remaining of this lesson, will be about estimating uncertainty or estimating dispersion of this estimator itself. Let's see. Right, so the long run mean was this expression, and now I'm trying to find out what is the dispersion or uncertainty around this value, right? And it's nonlinear, so I'm going to use delta method, and that's what's coming next.